Since the beginning of this year, the problems that we've done have all involved constant velocity, with the exception of a few graphs where I've asked you to find what the shape of the graph means. Any calculation that we've done, though, has involved one equation involving constant velocity, v is equal to delta d over delta t. Today we're going to look at acceleration. We know intuitively what acceleration means, right? Acceleration means speeding up, or for that matter, slowing down. What's the real definition for it, though? Not the intuitive thing, not the way that we kind of understand it commonly, but the real definition for it. Well, acceleration is the rate of change of velocity. We talked about a rate once before. The rate of change of position was change of position over change of time. The rate in change in velocity is acceleration. It's going to be change in velocity over change in time. Anything that's a rate has time on the bottom, and then whatever it's a rate of on the top. Here's the main equation for acceleration. Now, what units do you think we'd use for acceleration here? Now it becomes especially important that we start using standard units for position and displacement and time. Because in acceleration, Stephanie, I'm going to always use what units? Good. Meters per second squared. If you use kilometers for distance or for position or for displacement, then you're not going to get meters per second squared. You might get kilometers per second squared, and that's not a normal unit to use. Okay, we always want to be meters per second squared. So if it's involving acceleration, always go back to those standard units. What do you think about a vector or a scalar? Do you think there's a direction associated with acceleration? What do you think? Yeah, it's a vector. There is a direction, right? When I drop this pen, it accelerates. It doesn't just accelerate, it accelerates downward. It's not random. It falls downward and speeds up in the downward direction always when I drop the pen. So acceleration is a vector. And the direction of that acceleration is the same direction as the change in velocity. So we've just gone from one equation to two equations. Now we know v equals delta d over delta t. Now we know a is equal to delta v over delta t as well. But here's the day when you're going to learn probably the most equations in one single day ever for the rest of your lives. There's a bunch more here that are also valid whenever we have acceleration. D is equal to VIT plus 1/2 AT squared. What does delta D mean? That's not new. You guys know what that means. What does delta D mean there, Derek? Yeah, Chris? Displacement, good. So the displacement of an object experiencing acceleration is VIT plus 1/2 AT squared. What's VI mean? Initial velocity. What's T mean? Time, right? A is acceleration, T squared is time squared. All right, there's one. Here's another one. D is equal to VFT minus 1/2 AT squared. So you can get the same displacement, but this time using the final velocity as opposed to the initial velocity. VFT minus 1/2 AT squared. Note the difference here, plus and minus. Here's another one. D is equal to VI plus VF over 2 times T. This one's valid involving acceleration, but yet you don't even see acceleration in the equation. That's okay. Something is speeding up, you might not know its value, the value of the acceleration. It's still acceleration. One more. VF squared is equal to VI squared plus 2AD. What does VF stand for? No, but you're real close. VF does not stand for final velocity. Look at it carefully. Look at it closely. VF stands for what? Oh, who's going to get this? Who's going to get this one? Nope. VF squared. Okay, I'm asking what VF stands for, not VF squared. It's not final velocity. It's not final velocity squared. VF stands for... Alana, looks like you're ready to go here. No? Yes. It's final speed. How do you know it's final speed, Alana? Go ahead. Yeah, there's no half arrow over top of it, right? It doesn't have the vector sign over it. So this would be final velocity. This would be final velocity. This would be final speed. What's this one going to be? Initial speed, right? Bottom line is this, guys. We use these equations, solve for VF or solve for delta D, whatever. We're going to get the direction. This one we solve for VF, we won't. We won't know what direction it is. Okay, we'll have to figure that out some other way. 5 new equations today. You went from 1 to 6 in a matter of minutes. That's okay. Okay, it doesn't need to complicate things. We've got all of these on our data sheet. Understand all of the ones that I've given you today, all of the ones that are circled in blue here, are all valid at the same time. They're all valid whenever an object experiences acceleration. It doesn't have to mention the word acceleration, but if it's speeding up or slowing down, those are the valid equations, all the ones circled in blue. There's one more that we already learned. We're going to make this red, delta D over delta T. That one is valid when the velocity is constant, not when it's acceleration. We are, from this point out, going to call this my group A equation, and we're going to call the ones that are circled in blue here my group B equations. My group A equation, there's only one of them, is valid for constant velocity. My group B equations, all of them, are all valid when you have acceleration. So, if it's a constant velocity problem, you know which equation you're going to use because there's only one of them. If it's an acceleration equation, there's 5 choices. How do you know which one to use? Well, write down your givens and see which one fits the givens the best. Listen, if you can't figure it out, guess. As long as you're guessing within the right group, group A or group B, guess. And if your guess is wrong and it doesn't work out for you, then what should you do? Guess again. That's okay. Sometimes it's going to be obvious to us which equation we're going to use first. Sometimes it's not. If you can't get the right one first, try one, as long as it's in the right group. And if it doesn't work good for you, try again. Okay, I promise you, if you use it properly, you won't get the wrong answer by guessing the wrong equation. You just won't get an answer. You have too many unknowns. All right? Got a whole lot of examples today, but we'll do one at a time. Do one example, give you some time to work on a couple questions. Another example, time to work on some more questions, and so on. Okay, first example is 1.12 on page 47. It says, I'll let you guys read this one just for a second, make sure that everything makes sense to you, and then we'll take a look at it as a group here. All right, we read this. A hybrid car. What's a hybrid car? Not that it's really relevant to the question that it's a hybrid car, but just out of curiosity, what is a hybrid car? What's the difference between a hybrid car and my Grand Caravan or my Ford Escape? It's quieter. Yeah, it is. Yeah. Why is it quieter? Like what? Yeah, what's that? It runs electrically and gas powered. It runs electrically when it can, and then it runs gas powered basically when there's not enough electricity to do what it needs to do. Okay, so it ends up being better on gas because when you pull up to an intersection and you stop, what happens? It turns off. Doesn't need to be going. So it's not running when it's sitting at a stoplight. Put your foot on the gas pedal, the electric motor kicks in, you accelerate, and then later on, your gas motor kicks in. It's better on gas, it's quieter, all kinds of good things about it. Anyways, it has an initial velocity of 10 meters per second, accelerates at 3 meters per second to the east. So 8 meters per second squared to the east. How long will it take the car to acquire a final velocity of 25 meters per second? All right. Here's something. 10 meters per second. Let's make east positive, by the way. What's that? What's 10 meters per second? Is that a displacement? Yes or no? Shake your head. Shake your head this way, this way. Displacement? No. Okay. Ali, is it an acceleration? 10 meters per second? No. Okay, what is it then? Good. It's a velocity. But what velocity is it? Is it V? Is it VI? Or is it VF? Remember, V is the constant velocity. VI is initial. VF is final. Seth, your hand was up? It's V what? VI, yeah. It's the initial velocity. This is how fast it's moving at the beginning of this problem. It accelerates at 3 meters per second squared. What's that? What's that? Good. Acceleration. Positive because it's to the east. Something's 25 meters per second squared. What's that? Good. Final velocity. What are we looking for here? What's the unknown? Second? Good. Time. All right, quick question here. Is this a group A or a group B? In other words, is this constant velocity or does this involve acceleration? I think it's pretty clear, right, when we look at our givens, which one this is. Group A or group B, Lewis? It's B. It involves acceleration. But you know what? We've got 5 equations that we can use for acceleration. That's a lot. Which one of these equations seems to fit our givens the best? Remember, we had given to us A, we had VI, we had T given to us, and we wanted to find VF. Which of these blue equations here fits those givens the best? Which one do you think is going to work the best? Was the time we're supposed to find? Okay, so we had VF. Honestly, it doesn't really matter which ones you have and which one you're looking for, as long as you identify the right variables, right? But you're right, thank you. So we're looking for time. Doesn't change which equation we're going to use, right? Look at them, guys. Look at them. Look at all 5 of these. I want everybody to commit to something. Okay, commit to, call this number 1, number 2, number 3, 4, and 5. Give you 30 seconds. Everybody's got to commit to one of those equations. Okay, Ryan, which one are you committing to? Doesn't matter if you're picking the right one. Don't worry about it, okay? 4? Okay. So D is equal to VI plus VF over 2 times T. Let's try that. Glad you picked that one, Ryan. Yeah, we have an initial velocity. We have a final velocity. 10 plus 25 over 2 times the time of, oh no, we're looking for time. Oh, and we don't have displacement. Glad you picked that one. You know why? Because it doesn't work. I'm glad you picked one that doesn't work. Okay, the point that I want to make with this is that it's okay to pick one that doesn't work. He didn't pick an invalid equation. He picked one that was valid. It's perfectly valid. It's just as valid as the one we're going to use. What happens? How do we know it doesn't work? Because we have 2 unknowns. It just doesn't work. So what happens at this point? Pick another one. Okay, pick another one. Zach, which one did you pick? Number 2, so VFT minus 1FAT squared. Okay, let's take a look at that one. No, sorry, VIT plus 1FAT squared, right? Okay, so let's take a look at that one. D is equal to VIT plus 1/2 AT squared. I think we might run into the same problem. We know what VI is. We don't know what T is. We know what A is. We don't know what T is. Too many unknowns. Now, there is a way to make these work, the one that you picked and the one that Ryan picked. There's a way to make both of those work, but it's not the simplest way to solve the problem. Which one did you pick, Lewis? 1? A is equal to delta V over delta T? I'm sorry? Right. So time goes up to the top by multiplying by time. And then we're going to solve for time by taking the a down by dividing. So delta v over a. Delta v, vf minus vi, 25 minus 10 over a is 3.0. Hey, that works, doesn't it? 25 minus 10 is 15, divided by 3 is 5.0 seconds. So two people gave me equations that were perfectly valid. Perfectly valid. They just didn't work because we had too many unknowns. The last person gave me an equation that was also perfectly valid, but no better than the first two, but also worked because it fit the givens the best. Okay? I really want you to get this here, guys. You don't have to have the right equation right off the top. If you spot the right equation, hey, it saves you time. Okay, instead of taking you a minute and a half to do the question, it takes you a minute to do the question. You've saved 30 seconds of your life. If Zach picks equation number 2, it's going to take him 30 seconds longer to do the question. But he's still going to do the question, right? Who cares? Okay, I know that, Zach, that's 30 seconds of your life that you're never getting back. But you're young, and I think you'll survive. Right? Me, on the other hand, I'm 42. I don't want to waste 30 seconds because I don't have as long as you guys left, right? I've only got another 70 or 80 years left. But you guys have all the time in the world. Okay, 30 seconds, who cares? Don't worry about picking the right equation. Just don't pick v equals delta d over delta t. Don't pick a group A equation for this because it's not valid. Go ahead. Okay, good question. I didn't show you the units here, and I should have. Okay, I should have. This is meters per second, right, on the top. Divide it by meters per second squared, right? How does that give us seconds? Well, good question. When you divide by a fraction, right, that's what I'm doing there. Dividing fraction divided by fraction, you end up multiplying by the reciprocal. So that's the same thing as saying meters per second times seconds squared per meters. Does that make sense? Meters on the top, meters on the bottom cancel. Seconds on the bottom, one of the seconds on the top cancels. So what are we left with? Seconds. Okay. Is that good, guys? All right. Excellent. Well, let's take a look at the practice problems that go along with example 1.12 on page 47. Again, take a look at each of these questions. Identify if it's group A or group B. If it's group A, use v equals delta d over delta t. If it's group B, there's 5 equations. See if you can identify which equation to use first to save yourself that 30 seconds of your life. But if you can't, that's okay. Just pick one. If it doesn't work for you, pick another one. No big deal. Okay, we'll give you some time to work on that, and then we'll take a look at it as a class. Let's take a look at number 2 as a group here. It says an elk moving at a velocity of 20 kilometers per hour accelerates at 1.5 for 9.3 seconds until it reaches its maximum velocity. What's its maximum velocity? I don't care about the kilometers per hour. Meters per second is fine right now. Is this a group A or group B problem? Before we go anywhere else, group A or group B? Constant velocity or acceleration? What do you say for that one, Tony? Constant velocity or is it acceleration? Question number 2 there. I'm sorry? No, not group A. It's group B. It's acceleration, right? It's speeding up. The elk is speeding up. It's accelerating. It's got to be group B. So we know we have 5 equations that we're allowed to use. Pick any one of those 5. But let's write down our givens to see if we can narrow it down among those 5. We have a VI of 20 kilometers per hour. Although we know we're going to want to convert that to meters per second. An acceleration of 1.5 meters per second squared, a time of 9.3 seconds. And we want to find VF, the velocity at the end of it. Which of those 5 equations do you want to use here? Again, we have, you know what? I was going to say we have VI, we have VF. We don't have VF, do we? But if that's the one we're looking for, we'll count it. Okay? So look at these. You got VI, got VF, got A, got T. Which one do you want to use of the group B equations here? Let's use equation 2, VIT plus 1 half AT squared. All right, let's give it a try. Oh yeah, let's go through this here now. VI, we got it. T, we got it. Okay, looking good here. A, we've got it. T, we've got it. Perfect, right? That's going to allow me to solve for, oh wait, displacement. It's not what we're looking for. Did we get the wrong answer here? We didn't get the wrong answer. We just got some other answer, right? We got displacement, not final velocity. Now, you could use that displacement along with another equation to find the final velocity. That would be okay. A quicker way to do it from the beginning would have been to say A is equal to delta V over delta T. Rearrange it to solve for delta V. Let's get that. A is 1.5. Delta T is 9.3. That's going to work out to be 13.95. 13.95 meters per second. We want to find the final velocity. Well, we know that delta V is equal to VF minus VI. So it becomes delta V plus VI. Take the VI over by adding. Delta V is 13.95. Can't write 13 for some reason today. 13.95 plus 20 kilometers per hour is what in meters per second? Is it 6 or something like that? 6 point something? 5.55? So what does that work out to be? 19.45. We'll round that to 19 meters per second. Lewis, when you calculated displacement there, did you go with that and use displacement to find? Oh, okay. Okay. So guys, you understand now? Lewis got displacement here. Okay. We abandoned that and went to A is equal to delta V over delta T, but we didn't need to because we could have found the final speed by saying VF squared is equal to VI squared plus 2AD. We knew VI right from the top. We knew we knew VF right from the top. No, we didn't. We were looking for that. We knew A right off the top. We didn't know D right off the top, but Lewis found it for us. So we could have turned around and used that equation. I just chose to use this one because I think it was a little bit simpler, but it's no better. Would have got you the same answer. They're all valid equations. If they get you an answer, it's got to be the right answer. Okay? Well, if you're dealing with this squared, you'd have to square root to get VF. Okay. We haven't dealt with this equation really other than showing it to you, so that'll come tomorrow when I'll show you how to rearrange that one. A little bit uglier. Okay, here's what I want you to do for homework, guys. Okay, I have not yet given you the next example here, but what I'd like you to still try to do is do the next 2 practice problems on page 48 for homework, okay? It's the same basic idea, it just may be a different equation, one of the other 4 equations that are valid, okay? Okay, that's it for today, guys.